Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today starts on page 27 and it ends on page 33 from the textbook Chemistry 11 in Focus, and it deals with the following concepts: atomic radius, trends across a period, atomic and ionic radii, ionization energy, and trends down a group. Systematically arranged by the great Russian scientist Dmitry Mendeleev, 1834 to 1907. The periodic table is a vast and intriguing storehouse of knowledge for scientists and students of science. Mendeleev arranged the elements in the periodic table based on their atomic masses. Each row starts on the left with the element having the smallest atomic mass, followed by those with higher ones to the right. Every new row beneath starts with an element having similar chemical properties to the one above. A sound knowledge of atomic structure and systematic arrangement of atoms in a periodic table is essential for any student who aspires to excel in chemistry. Atomic structure, as it relates to electron configuration, provides useful information about an atom's radius, its ability to gain or lose electrons during chemical reactions, and the energy changes accompanying these processes. Comparison of the atoms and their radii can be used to predict the relative reactivity and give useful information on the amount of energy absorbed or liberated during chemical changes. Now, what is atomic radius? Atomic radius can be defined in two ways. Now, for this one here, the atomic radius is the distance from the center to the end of this atom here. And this is called its atomic radius. The other definition is if you took two of these atoms and you put them to touch each other very lightly, and you measure the distance between their centers and divide that distance by 2, that is another way of finding the atomic radius. Now, over here, we are seeing a small part of the periodic table, and it shows elements from groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A of the periodic table. And it also includes elements from period 1, period 2, period 3, period 4, and period 5. Mendeleev, as we're told, started arranging the elements in the periodic table by putting the one that is lightest at the end here, followed by those that are heavier on the right here. For example, in this case here, sodium has an atomic mass of 23 AMU. Magnesium has an atomic mass of 24 AMU. Secondly, when he started a new row, let's say he started this row here or period here, he put the element that has similar chemical properties as the one above it. In this case, if you had a group of all of these elements, then he would pick this one and put it beneath that one there because sodium and potassium have similar chemical properties. Why knowing atomic radius is important for us? It tells us about the size of the atom. Here we're using space-filling models to depict the radii of these atoms there. And I want you to look at some trends there. As you go down any group, you can find that the atomic radius increases downwards. As you move across a period, you can see now a different trend where the atomic radii are decreasing as you move across the group. So atomic radius tells us about the size of the atom, and that can help us to predict some physical and chemical properties. For example, sodium has an atomic mass of 23 AMU. And aluminum has an atomic mass of 27 AMU. Now, Even though this has an atomic mass of 23 AMU, it is larger in size, has a bigger atomic radius than aluminum. So aluminum now, if you compare the densities of these two, aluminum will be denser than sodium. Now, if you compare these two here, you can see potassium has a bigger atomic radius, a much bigger one than sodium. That means that the outer electrons of potassium will be held farther away from its nucleus than the outer electron of sodium away from its nucleus. It means the ability of potassium to lose electrons will be greater than that of sodium, and therefore the element potassium will be more reactive than sodium. So these are some of the chemical and physical properties that atomic radii can help us to predict. We want to see now, why is it that as you move across a period, the atomic radius decreases from left to right? We use these four elements here. They're in the period 2 of the periodic table: beryllium, boron, carbon, and nitrogen. These are the respective number of electrons and protons found in these atoms here. You can see, of course, the number of protons and electrons are equal in every case because every atom is electrically neutral. We do not include neutrons at this point because neutrons do not affect atomic radius. And of course, this is the way the electrons are arranged when you do their electron configuration, K element shell, 2 in the first, 8 in the other one, 8, and whatever is left goes there for the small atoms. Now, what we're doing here, we're drawing the Bohr-Rutherford diagrams for each of these elements here. So we have this atom here of beryllium. Doing the electron configuration, we put 2 electrons in the first shell here. That's the first shell. Since we are having only 4 electrons, the 2 will go there. If the same thing is done for boron, 2 will be here and 3 will be there. Carbon, 2 here, 4 there. Nitrogen, 2 here and 5 there. 2 important things I want to draw your attention to. You see this inner shell here. We will talk later on about something called shielding due to the inner core electrons. This is a nucleus here. And the nucleus of any atom is exerting an attractive force on the electrons. And that is what keeps the electrons in place. It is the attractive force from the positive nucleus on the electrons, the core electrons, as well as these outer electrons here. Now, because we have this shell inside here, these 2 electrons are found here, they have a shielding effect on the outer electrons there because they're intervening between this nucleus here and these outer electrons. So the effect of the proton on these electrons here is less because of the presence of these. If you remove these, then these will bear the full brunt of the effective force from the nucleus here. So right now we consider the inner shell electrons as having shielding properties here. This one is shielding 2 electrons from the outside. This is shielding these 3. These shielding those 4. These shielding those 5 there. Another important point is this. These 2 electrons are very, very close to the nucleus. So if you have 2 charges that are opposite and they're very close to each other, they can neutralize each other. So what we will assume here is this. Because of the proximity of these 2 electrons to the nucleus here, we'll assume that 2 of these protons will get neutralized by these 2 electrons, and we'll say that 2 of these electrons get neutralized by those 2 protons in a mutual way. So tit for tat. So we'll draw another set of diagrams where we show that these 2 protons are not there anymore and these 2 electrons are not there anymore. Same thing will happen here. So the next diagram that we'll draw will show only 2 protons, and this shell here will be absent. This one will have 3 protons. This shell will be absent. This one is going to have 4 protons, and this shell will be absent. That will have 5 protons, and this shell is going to be absent. So this is our next diagram here. So what we will say is this. We will say that effective nuclear charge that's left on each of these nuclear It'll be 2 plus here, because it's 4 before. 2 of them have been neutralized. This will be 3 plus, 4 plus, and 5 plus. So effectively, what's left of the nuclear charge is 2 here, 3 here, 4 here, 5 here. So these 2 electrons here are now under the influence of these 2 positive charges here. Not to say that those things are not there. Not to say that those 2 electrons are not there and those 2 protons are not there, but their effect has been negated. So here we have 3 positive charges attracting 3 electrons, 4 positive charges attracting 4 electrons, 5 positive charges attracting 5 electrons. Another point I want to make about these shells here. See, for grade 11 chemistry, you're told that these are like shells. They're like circles there. Huh? But when you do grade 12 chemistry, you'll find that this whole thing here is a spherical electron cloud. These shells here can contract and expand. So depending on how forcefully these nuclei here are attracting these electrons, these shells here can contract. So we'll discuss now Coulomb's law, and Coulomb's law will enable us to tell which one of these nuclei here will pull in the electron shell closer to the nucleus, to itself. So let's look at a quick look at Coulomb's law. Full name, Charles Augustin de Coulomb. So look at Coulomb's law. What Coulomb is saying is that the force between 2 charges, say Q1 and Q2, is directly proportional to the magnitude of the charges, but it is inversely proportional to the distance squared. Let us look at a typical example of what is happening here. Here we are having 2 charges here. Obviously, because they're oppositely charged, there's going to be an attractive force here. So now, if we substitute that inside here, 1 and 1, and this distance, we have a certain force here, F. Let us call that F1. Now, if you double the charges now, I make this D2, but D2 is same as D1. The only thing you've done is to double the charges here. Now, if you're to find the value of F2, you find we have to double the charges here, but D stays the same. Definitely, therefore, what we say, which one is bigger, F2, F3, or F1? F3 will be greater than F1 because of bigger charges. So we have dealt with the magnitude of the charges. Let's look at distance now. Here we're having the same magnitude of charges in both cases here, but we changes this distance here. So because we're making this bigger now, definitely this force here becomes smaller. So that's Coulomb's law. So let's apply Coulomb's law to tell us now which one of these electron shells here will be pulling closest. So here I have 2 positive charges and 2 negative charges, 3 and 3, 4 and 4, 5 and 5. So who can say in which case the electron shell will be pulled closest to the nucleus? If you say that of nitrogen, then you're correct. The one that will pull it in the least will be this nucleus here because of the smaller charges here. So it's going to pull it into a certain degree here. This one will do it a little bit more because the greater number of charges here. This one more, and this one the most. So if you draw a new picture now, a new diagram for that, we'll end up with a new diagram like this. See? So these will be the respective atomic radii for each of those atoms. And you can see that as you move from left to right of a period, the atomic radii decrease. It's all summarized here. Okay? So read this. Since it is a nuclear charge of each atom that attracts the electrons, it can be concluded, according to Coulomb's law, that the attractive force on the outer electron by its nucleus increases from left to right of a period. It should be noted that the electron shells can contract or expand depending on the force of attraction from the nucleus on them. How close to the nucleus the electron shells are attracted will ultimately determine the size of the atomic radius, which is indicative of the size of the atom. After analyzing the Bohr structures, it can be inferred that moving from left to right of the period, the outer electronic shells of the atoms will be pulled progressively closer and closer to their nuclei, rendering their atomic radii smaller and smaller. So that is why, as you move from left to right of the periodic table, the atomic radius decreases like that. Next, we'll study ionization energy.